So earlier in this unit, we learned how to convert between grams of a substance and moles of a substance using its molar mass. But that type of conversion only applies when you're dealing with pure substances, and in chemistry we're often dealing with mixtures. One particular type of mixture that you will encounter really frequently is one that we've already talked about a little bit, known as an aqueous solution. So an aqueous solution is a homogeneous mixture in which some substance is dissolved in water. So that dissolved substance we call the solute. And water is what we call the solvent, is what that substance is dissolved in. So the solute dissolves in the solvent. There are other types of solutions that have different solvents. By far the most common one that we're going to encounter is the aqueous solution, which just means that water is our solvent, that something is dissolved in water. So when we have this type of mixture, we can't talk about quantities using mass and molar mass because it's not just one pure substance. Some of it is water and some of it is whatever is dissolved in the water. So we need a different way to figure out how much solute is present in our solution. And we measure this in terms of what's known as concentration. So in the most general sense, the concentration to a chemist is the measurement of how much solute is dissolved in a solution. There are other ways that this term can be used, but for now that's what we are talking about. And very generally speaking, we can refer to a solution as concentrated to mean that it has a high concentration of stuff dissolved in it. So lots of dissolved solute. Or we can refer to a solution as being dilute to mean that it has a low concentration or just a little bit of the solute dissolved. And what exactly constitutes high or low or a lot or a little is very context dependent. And these are very just qualitative terms anyways. So generally, if I just say something is concentrated, I want you to know that it's a high concentration. Often you'll hear this in the context of concentrated acids to denote that they are particularly hazardous because there is a lot of acid in that solution. Or a dilute acid would be much less hazardous because there's not actually as much acid in the same volume of the solution as a whole. So the term concentration is still pretty general because there are lots and lots of ways that we can measure the concentration or lots of different units that we can use to express concentration. The one that is generally used in chemistry is known as molarity. It is symbolized with a capital letter M. And molarity is specifically how many moles of solute are present in 1 liter of solution. So you will often see this expressed as moles per liter or capital M. Those two things can be used interchangeably as the unit. So what molarity gives us is essentially a moles to volume ratio for a particular solution, that if we have a whole liter of it, this is how many moles of solute are present in that solution. If we have less or more than a liter, we can scale up or scale down proportionally to figure out how many moles of substance of the solute that we're actually dealing with. Usually it's going to be the solute that is the thing that's reacting in a chemical reaction. So we saw in our last unit that something like a precipitation reaction is occurring between substances in aqueous solution. So those are the solutes that are reacting. So it is important to know how much solute is present to know how much of that reaction can happen. So let's look at a few examples of how we can calculate molarity and how we can use molarity. So first up, here we go. So what is the molarity of a solution that contains 0.45 moles of sodium chloride in a volume of 250 milliliters? So we are looking to calculate the molarity, and we know that molarity is moles of solute per liter of solution. So moles of solute, so let's make that bigger. Moles of solute is given to us directly. That's easy. The liters, we're not directly given, we are given a volume in milliliters. So we are going to have to convert that. We know that 1 liter is equal to 1,000 milliliters. So if we want to convert that 250 milliliters, we're going to put 1,000 milliliters on the bottom, 1 liter on the top. So that is going to be 0.25 liters. And now this is really the value that we want to be using when we go to calculate our molarity. We always need to have moles of our solute and the volume of our solution in liters. So to calculate the molarity, once we've done that one little unit conversion, we're just taking 0.45 moles and dividing by that volume in liters. So this gets us a molarity of 1.8. So we would say that that is a 1.8 molar solution. Next up, kick the complexity up one notch. What is the molarity? Let's just do this on the second page, I guess. What is the molarity of a solution created by dissolving 25 grams of sodium hydroxide into 500 milliliters of solution? So this one is a little bit more realistic in terms of how we actually make solutions in the lab. We are usually starting with a solid solute that we're going to weigh out on the scale, and we're going to put that into some amount of water to end up with a solution once that solid has completely dissolved. And so we can calculate the molarity of that solution. And this is where we're going to start really using parts of this flowchart that you received. So right now, we are kind of up in this corner. So this is like the top left corner if you're looking at the whole page. What we currently know, we know the grams of our substance. So we are told that we have 25 grams of sodium hydroxide. We are told we have 500 milliliters of the solution that we are dealing with, and we are asked to calculate molarity of that solution. So we are asked, what is the molarity of that solution? Anything went away? There we go. So we know that molarity, It's not the thing I wanted, that's the thing I wanted. Molarity gives us a relationship between moles of our substance and volume of our substance. We don't know the moles currently, we know the grams. So wherever we kind of know things, we need to follow the path on this flowchart in order to get to our answer. So before we can solve this, we're first going to need to get from grams of sodium hydroxide to moles of sodium hydroxide, and we do that using the molar mass. So that's going to be our first step. It's going to be to find how many moles of sodium hydroxide are in 25 grams. So we have 25 grams of sodium hydroxide. We can find the molar mass by looking at our periodic table and adding together the mass of sodium, oxygen, and hydrogen, which gets us a total of 39.997. So that is the number of grams of sodium hydroxide that are equivalent to 1 mole of sodium hydroxide. We want the grams on the bottom so that that cancels out, and we are left in units of moles, which is where we want to be. So that gets us 0.62504 moles of sodium hydroxide, keeping some extra sig figs for now. And then once we have that, we can use that to find our molarity. So now we have found moles. We have gotten this value using our molar mass. So at this point, we know how many moles are in how many, or in what volume. We're given it in milliliters, so we'll need to convert that. And that is going to allow us to solve for our molarity. So the only other thing we need to keep in mind is that we do need to convert that volume to liters. So our molarity is going to be the number of moles we just found, 0.62504 moles divided by 500 milliliters. We'll divide that by 1,000, since there are 1,000 milliliters in 1 liter, which gets us a grand total molarity of 1.25 molar. So remember, we needed to convert this to liters. This is why we did this little piece down here to get our final answer. So last but not least is another similar question, just solving for a different quantity. So this one is asking you what mass of calcium chloride must be dissolved in a volume of 100 milliliters to produce a solution with a concentration of 0.5 molar. So once again, let's move this new copy of this guy down here. Oh no, it's gonna go poorly. No, that's fine. We don't need that part, but what we know this time is we know the molarity, we know the volume, those are given to us initially, and what we're asked to solve for, what we're asked to solve for is what mass of our substance do we have to dissolve in order to produce this solution? So this is probably the most like real world application of these 3 examples. Generally, when you're going to go do an experiment, you know you need a certain amount of solution at a certain concentration. And, this is how I prep your labs. If you need 0.5 molar calcium chloride and we need 100 milliliters for you to all be able to do it, I do this calculation to be able to prep your lab. So once again, we're going to need to kind of follow our roadmap here, follow our flow chart to get from the information we have to the information we're actually looking for. And we can see that we have to pass through moles. So we can use our molarity and our volume in order to do that. So the first thing we're going to do is find moles of calcium chloride. that we need in order to make this solution. So again, we always need to convert our volumes to liters here. So 100 milliliters divide by 1,000 to do that conversion is 0.1 liters. We know that our molarity is 0.5 molar, which is 0.5 moles per liter. So if molarity is moles per liter, and we multiply by how many liters we actually have, liters cancels liters, and that's going to leave us in units of moles, which is exactly what we are looking to do in this first step. So what this tells us is that in order to produce this solution that we want, we need to dissolve 0.05 moles of calcium chloride into the 100 milliliters of solution. And then our second step, our last step, we now know, what color haven't I used? We now know moles of A, so we can easily convert to grams using the molar mass. So our molar mass is going to be the mass of calcium plus 2 times the mass of chlorine for a total of 110.984. So we have 0.05 moles of calcium chloride that we are looking to convert. Since we are starting in moles, we want moles on the bottom of our conversion factor and grams on the top. So the 110 point, what was it, 984 is going to go on the top, and that is the number of grams that is equivalent to 1 mole. So we find that that is about 5.5 grams of calcium chloride that we would have to dissolve into 100 milliliters to make a solution of 0.5 molar.